I want to do a few problems that will be applications of Newton's third law, but I'm going to start with one. Just what does a scale measure? When you think about that, what's going on? So you've got a floor here, you have a scale sitting on top of it, and then maybe you've got a person standing on top of it. And if you say the scale measures your weight, well, that may not always be the case. In this case, if it's a scale sitting on a nice stationary floor, it will measure your weight. But your weight is supported by the scale. It's the earth pulling down on you. How does that show up as something on the scale? Well, let's start with some free body diagrams. Okay, then we'll start with a free body diagram for you. So this would be you. All right, you've got a force acting downward on you, the force of the Earth's gravitation, and you have a force pushing up on you. And I'm going to write this as a normal force of SY, the scale on you. And then I'll do one for the scale. Okay, so there we've got the scale. The scale has a weight, so I should call this m sub y for the mass of u. It's going to have a weight that's the mass of the scale times the acceleration due to gravity. It's sitting on the floor. That'll be the normal force of the floor on the scale. And there's another force acting on it that we can understand if we consider Newton's third law. Whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. Okay, the scale exerted a force on you. That means you exert a force on the scale, and there will be this downward force on the scale. That's, let's see, this is the force of you on the scale. Okay, we called this a normal force of the scale on you. This is actually the third law partner to that force. Forces always occur in pairs acting on two different objects. Okay, in this case, you may have equal and opposite forces, but they're not third law partners. Equal and Newton's third law forces, let's try that again. Newton's third law forces, the pairs of them, have to be the same mechanism. If the Earth's gravitation pulls down on you, your gravitation, believe it or not, it exists, pulls up on the Earth. Now, the effects of those forces don't necessarily have to be equal unless the two objects are equal in mass. The force of the Earth pulling on you, it has an absolutely enormous mass and it pulls down on you, and you don't have that big a mass, so that force of the Earth pulling down on you can have an effect on you. An equal force acting on the Earth has virtually no effect on the Earth. Okay, it's enormous. It's not going to react. Remember, the acceleration of an object is the force acting on it divided by the mass, and if the mass is absolutely enormous, it's not going to have a typical force, won't have much effect. Excuse me. So anyway, let's think about these forces here. Here's a good way to state forces for understanding Newton's third law pairs and be able to state them carefully. This is the force of the scale pushing up on you. Okay. Now, I had another force on here on the scale. I didn't draw it very well, but it's F sub ys That would be the force of U pushing down on the scale. Now, here's what I did. I had the scale and U up there. I swapped those and I swapped the direction. So I put U where the scale was and the scale where you were, and then I changed the up to a down. If you don't think there's a force of U pushing down on the scale, you can do an experiment. Lay on your back on a floor and have a small child stand on your stomach. Right? That small child is supported by the force of U pushing up on the bottom of their feet, and they most definitely exert a downward force on you. If you ever have a small child stand on your stomach, you'd notice that. If you don't have a small child, just get a concrete block, one of those ones that weighs about 35 pounds, and set that on your stomach while you're laying on your back, or have someone set it on there for you, and you'll definitely feel that force pushing down on you. Now, when the scale is just sitting there on the floor, when it's only got these two forces acting on it, its own weight and the normal force of the floor, it doesn't read anything. What it responds to is the force of U standing on the scale. So let's do some problems that put this to the test. A 59-kilogram woman stands in an elevator that is accelerating downward at 3.1 meters per second squared. What force does she exert on the floor? Okay, now we're taking a scale out of the picture, but it seems to me you might have a homework problem that does have a scale in the picture. So it's accelerating downward at 3.1 meters per second squared. Let's figure this out. So here we've got an elevator. All right, it's got a little, nope, let's just not have the scale. We'll just have this 59-kilogram woman in there. There she is. And let's consider a free body diagram for her. So there's her mass, which is 59 kilograms, times g, and there's a normal force pushing up on her. Now, the third law partner of that normal force, the normal force is the force of the floor pushing up on the woman at her feet, pushing up on her feet. The third law partner of that would be the force of her feet pushing down on the floor. That's what the question is. But if we figure out the magnitude of the normal force, we'll know the magnitude of the force that she exerts on the floor. So let's just figure that out. Let's see, we could let up be positive, and we can say that N minus mg equals ma. Now, if you only have one dimension going on, you can quickly convert it into a scalar equation. Just pick a direction to be positive, and that's that. Now, they said she's accelerating downward at 3.1 meters per second squared. I'm going to leave it just as ma for the time being, because who knows, we might switch it and have her accelerating upward at 3.1 meters per second squared. But we would just have n is going to equal mg plus ma, or it'll equal her mass times g plus a. Now, this got a minus sign over here because we know it's a downward force. This, we'll wait until we actually put in a value for a to assign a sign to it. We happen to know that it's downward, but it could be the other direction. This will be a more general expression. You could see off of this that if there's no acceleration, the normal force would equal her weight. and that would thus be also the force that she exerts down on the thing. If you had a positive value for the acceleration, so it was accelerating upward, then the force that the floor exerts on her would be larger than her weight, because you'd have G plus A there, and A would be positive. But in this case, she's accelerating downward. And so we can figure out what it is. It's going to be the 59 kilograms. I almost had her put on 20 kilograms of weight instantly there. 9.8 meters per second squared. We've only got 2 sig figs here. Minus 3.1 meters per second squared. A minus sign because she's accelerating downward, or the elevator is. Now, this had a minus sign when it was on that side, but when we add it to the other, it becomes positive. So anyway, whatever that turns out to be, actually, I think I'll distribute the 59 kilograms through there so we can see just how much of a difference this makes. All right, just her mass times G turns out to be 580 newtons, kilogram meter per second squared, and this ends up being about, let's see, 180 newtons. And so you'll end up with the normal force, which is the force of the floor pushing up on her, is going to be, if I write it to 2 significant figures, I'll use scientific notation, 4.0 times 10 squared newtons. Okay, or 400 newtons with 2 significant figures. Anyway, that's the force of the floor pushing up on her, but it's equal to the force she exerts on the floor. So that's how you solve that one. I don't know, there aren't very many elevators in Moses Lake and they're not very fast, but if you ever go to some place that has some tall buildings with some fast elevators, when they start going upward, they're accelerating for a short time. So this would be positive, and you can feel that in your body tends to remain at rest, and your knees sometimes bend when that happens to be the case. Okie doke, let's try another one. Oh, now we've got a scale. Okay, a 550 Newton physics student stands on a bathroom scale in an 850 kilogram elevator. That includes the mass of the student. Now we're given the weight of the student, but the mass of the elevator and student. So things are a little bit changed up here. As the elevator starts moving, the scale reads 450 newtons. Okay. Oh, as the elevator starts moving. Yeah, we don't know what direction it's going here. But it says find the acceleration of the elevator, magnitude and direction. Okay, now remember, the scale reads the normal, or the force that the student exerts downward on it. That's the third law partner of the force that the scale exerts upward on the student, which we've been calling the normal force. So if we were to make a free body diagram for the student, we'd have the student's weight downward and the normal force, which is the force the scale exerts up on the student, upward. And we can say, with positive being upward, that N minus mg is equal to ma. Now, N is the force of the scale upward on the student, but the scale reads, the force of the student pushing down on the scale And in this case, we happen to know that, at least in part A, that's 450 newtons. We know that the student has a weight of 550 newtons. So what we've got for this first part is that the normal force is 450 newtons, the student's weight is 550 newtons, and that'll equal the mass of the student times the acceleration. Well, I get minus 1.0 times 10 squared newtons. I've only got 2 sig figs, and that's a way to show it. And that'll equal ma. I've got a negative acceleration. We don't have negative mass in physics. Okay, so I never did figure out the mass of the student, but if 550 newtons is equal to the student's weight, then the student's mass would equal 550 newtons over 9.8 meters per second squared. Maybe I never figured that out. Guess I didn't. Okay, I get about 56 kilograms for the mass of the student. So the acceleration in this case would be minus 1.0 times 10 squared newtons divided by 56 kilograms, or about 1.8 meters per second squared. And again, a newton divided by a kilogram. A newton is a kilogram. Meter per second squared. The kilograms divide out and you get meters per second squared. Be thinking about that all the time and always be writing down the units with things. Okay, I guess that was part A. Alright, part B says, what is the acceleration if the scale reads 670 newtons? Oh, well, the scale reads the normal force, so I can still do this. N minus mg equals ma. N is 670 newtons minus 550 newtons. That's the mg for the student. That will equal, looks to me like 120 newtons. Check that. Then that would equal the mass times the acceleration. I can see in this time the acceleration is going to be positive, so it's going to be going up, and it would equal 120 newtons over our 56 kilograms for the student. Which is about 2.1 meters per second squared. Okay, let's see. If the scale reads 0, should the student worry? Well, here's what that means. If the scale reads 0, that means the student is not exerting a downward force on the scale, which means the scale is not exerting an upward force on the student. And so what we would get in that case is minus mg is equal to ma, or the acceleration in that case happens to be minus g. That means the elevator is in free fall. Should the student worry? Yes, the student should worry. The cables must have broken. So I don't know how you deal with a situation like that, especially if it was a 20-story building and you'd just gotten on at the top floor. So let's not worry about that right now. What is the tension in the cable in parts A and C? Well, we know the mass of the elevator and student there. We may have to make another free body diagram for this situation. Oh, I can just do it. No, let's see. I'll do it over here, and we can kind of ignore it for later things. free body diagram for just the elevator, it's supported by tension, and then I'll write M sub ES for the mass of the elevator and student times G is the downward force, with positive being upward again. I just say T minus M sub ES times G is going to equal M sub ES times A, or the tension will equal the mass of the elevator and student times, I'm going to bring this across and then factor out the M sub ES, it'll be G plus A. Okay, so I've got 850 kilograms for that combined mass. When the elevator is accelerating downward, whoops, I forgot a minus sign on this one. Somebody should have said something. Anyway, I would have 9.8 meters per second squared minus 1.8 meters per second squared, so about 8.0, and the tension would equal I get 6,800 newtons, kilogram meters per second squared. In the other case, when it was accelerating upward at 2.1 meters per second squared, the tension would be 850 kilograms times 9.8 meters per second squared plus 2.1 meters per second squared. And so the tension in that case, it ends up being 1.0 times 10 to the 4th newtons, or 10,000 newtons. Okay, so a fair amount more when it's accelerating upward. Okay, there's another one. Let's see, I'll flip this so that's not going to bother us. And what else is going on? Okay, let's lift a boulder out of a quarry. See what happens with that. A lot of the problems we do will be ignoring the, let's check out this one. We have a 750.0 kilogram boulder raised from a quarry 125 meters deep by a long uniform chain having a mass of 575 kilograms. It's uniform strength, but at any point it can support a maximum tension no greater than 2.50 times its weight without breaking. What is the maximum acceleration the boulder can have and still get out of the quarry? And how long does it take to be lifted out at a maximum acceleration if it started from rest? Let's think about this a little bit. And up here at the top, presumably the chain is attached to some sort of a hoist or something like that, and we got this great big long chain that extends down 125 meters. That's more than the length of a football field anyway, and at the bottom of it, it's attached to this boulder down here, which I have no idea how to show that, but 750.0 kilograms. Where do you think the tension in the chain will be the greatest? Well, at the bottom, the chain just has to support the weight of the boulder. But at the top, it has to support the weight of this entire length of chain plus that of the boulder. And so if it's going to break, it'll probably break up at the top. But we don't know that for sure. Let's see, it says it can support a maximum tension excuse me, no greater than 2.50 times its weight without breaking. Well, the weight of the chain is going to be let's see, 575 kilograms times 9.81 meters per second squared, which is 5,640 newtons. So that's the weight of the chain. The maximum tension in the chain is 2.5 times that much. So T max is going to equal 5,640 newtons times 2.5. And I actually get 1.41 times 10 to the 4th newtons for that. So 14,100 newtons approximately to 3 significant figures. Now let's do a free body diagram for this chain and boulder. They're just going to be a dot here, and look at the forces acting on it. There's going to be a tension acting upward on it that we're interested in being the maximum tension. So we'll have that. There'll be the downward mass of the boulder plus mass of the chain, and that'll be times G. And the tension doesn't just support the weight of this, it's also going to be accelerating upward. If I say positive is upward, I'll have T max minus mass of the boulder plus mass of the chain times G is going to equal the mass of the boulder plus the mass of the chain times whatever acceleration it's going to be given. Okay, well, we can kick this across. T max is going to equal, just take that across, and actually if I do a little factoring at the same time, I'll have two terms on the right side that have that mass as a common thing. It'll be G plus A. Oh, except what I should have done was just solve for the acceleration. Okay, let's do that instead. If I divide both sides by that total mass, mass of the boulder plus mass of the chain minus G, just imagine dividing this by, or both terms by this, that's going to be the maximum acceleration. And maximum tension is 1.41 times 10 to the 4th newtons. If I divide by that total mass here, I would actually get, I'm not going to show the calculations, but I'd get 10.6 meters per second squared for this, minus 9.8 meters per second squared for G, and that'll be about 0.8, and I'm down to one significant figure, so 9.81, but the uncertainty there is in the hundredths place. Here it's in the tenths place, so I just get down to 0.8 meters per second squared for that maximum acceleration. Okay, then it asks, how long does it take to be lifted out at maximum acceleration if it started from rest? Well, I'm going to slide up and kind of hide that, but I think we can solve that. For part B, it's going to be accelerating upward. I could say that y is going to equal y naught plus v naught y t plus 1/2 at squared. Okay, it's attached to this chain and it's accelerating upward. I can say y naught is 0, v naught y is 0, and the y that we're going to end up at is 125 meters, and that'll equal 1/2 at squared. So t squared, I don't know if that would show, t squared, squared is going to equal 2 times 125 meters divided by that 0.8 meters per second squared. And if you solve for t, you end up getting about just 20 seconds. So, and we're down to one significant figure, so that's about as close as you can call it. Alrighty. Well, that wasn't exactly a Newton's third law problem, but it sort of is. Here's one that involves Newton's third law. Let's see how this one can be dealt with. We have a 5.0 kilogram block and a 3.0 kilogram block placed on a frictionless surface. Oh good, no friction. And a 12 Newton force is applied to the 5 kilogram block as shown in the diagram below. Calculate the contact forces between the blocks and the acceleration of the system. Well, since you're pushing on both of them, you actually have to accelerate 8.0 kilograms, and we can calculate the acceleration easiest perhaps just by thinking of that. If you're pushing that way on these two things, you're going to accelerate both of them. There's no friction to worry about. So the force that you exert is going to equal the total mass being accelerated, 5.0 kilograms plus 3.0 kilograms. F equals ma, and so we can just figure out what the acceleration is like that. The acceleration will equal the 12 newtons divided by, and that's 2 sig figs. Actually, we'd have 3. It'd be 12.0 newtons, but we only have, oh no, we don't have that. Excuse me. On the bottom, we'll have 8.0 kilograms is what we'll have. So 2 sig figs top, 2 sig figs bottom. That works out to 1.5. And Newton is a kilogram meter per second squared, so it's meters per second squared. Okay, so there's the acceleration. Now, let's think about forces acting here. First, for the 5 kilogram object, let's do a free body diagram for that, and for the 3 kilogram object. What have we got going on here? For the 5 kilogram object, we've got a sideways force of 12 newtons. Then I'll just write that as F sub 12. Okay. We've got a downward force that's going to be m5 times g. Okay, that's the weight of it. We'll have an upward force from the tabletop or surface, whatever it happens to be. I'm going to call that n sub 5 just for the normal force on the 5 kilogram thing. And there's a contact force between the 5 and the 3, and I'll write that. Now, usually I put the tails on the dots, but I'm just sort of indicating this from, I don't know, where it's acting. This would be the force of, I'm going to write it as 3,5, the force of the 3 kilogram mass on the 5 kilogram mass. And it's that combination of forces that produces the acceleration. Well, one thing we know, this thing doesn't fall through the surface and it doesn't jump off the surface, and so the vertical forces combine to 0. If I really needed to know it, I could calculate it, but I don't. And if I say positive is to the right, I can say that the 12 Newton force minus the force of the 3 kilogram mass on the other one will equal ma. Okay. Well, I figured out the acceleration. That's 1.5 meters per second. So, let's see. I can say F12 minus ma is going to equal F35. I'm dealing with magnitudes now. The sign indicated the direction of that, but when I bring it over, it becomes positive. And this is 12 newtons minus 5.0 kilograms times the acceleration of 1.5 meters per second squared. That will equal, let's see, that's 7.5, so we'll have 4.5. 12 newtons minus 7.5 is 4.5. Will equal the force of the 3 kilogram object acting on the 5 kilogram object. Okay, that'll be the contact force. Now, 4.5 newtons is also the contact force of the 5 kilogram object acting on the 3 kilogram object. But I can show you that if you're unconvinced. In magnitude, that will equal the 5 acting on the 3, the magnitude of that thing as well. But let's do a free body diagram for this, the 3 kilogram mass. We'll have mass of the 3 kilogram thing times g. We'll have a normal force acting on the 3 kilogram object, and it's being pushed on by that 5 kilogram object, so this would be the force of the 5 kilogram object on the 3, and that's what produces the acceleration of the 3 kilogram mass there. Well, with positive being to the right, again, I know the vertical forces add to 0, so don't need to worry about them. But I'll have the force of the 5 kilogram object on the 3 kilogram object will equal the mass of that 3 kilogram object times its acceleration. Well, its acceleration is 1.5 meters per second squared, so I'd have 3.0 kilograms times 1.5 meters per second squared, and surprise, surprise, that ends up equaling 4.5 newtons. So first we solved it by just combining these things into a single mass, and then we individually solved those things knowing the accelerations. Okay, some Newton's third law applications, and then one involving a chain that wasn't so much a Newton's third law application.